So let's start the design of a comb drive structure. Here I've created two layers. One is comb and pads. So here I create them by adding new layers, and I can change the color here. Okay, the idea of changing the color is to differentiate between the layers. That's all the intention. So I can rename the layers here. So I've taken two layers and then I start creating the geometry. In the beginning, you may have to enable the command line. So you can enable the command line here. Once the command line is enabled, so here we get the command line which is at the bottom. So here I create the rectangle, the command rectangle, so 0, 0. So here I create the rectangle. So with the comb as the layer 0, 0, enter, and 100, 3. So here we have created a rectangle of length 100 micrometers and width 3 micrometers. Okay, so let's draw other geometries as well. 0, 0, 5, 53. So this creates a vertical diagram. So here I draw one more. 0, x point is 0 and the y point is 25. Enter, and 110, 28. So I have one more rectangle here. So here we are creating the outlines. So if we require a layer fill, so we can enable this by layer fill option. So we can as well create it with outline as well. Okay, so to keep it simple, let it be outline. So now we want to create one more rectangle. Here we create a mirror image. So I draw a mirror line. So here exactly it has to match the position at the top. So hence the mirror line is exactly in this middle. So considering this as the middle line, so the coordinates of the middle rectangle is 25 and width is 3 micrometers. So 25 to 28. So the mid position is 26.5. So I'm drawing the mirror line exactly uh, horizontal to that. So keeping that in mind, I enter these coordinates 0, 26.5. I need to draw a line in the x-axis. So naturally I increase the value towards the x-axis and then maintain y value the same. So this creates another rectangle which is a mirror image. So once this is done, so press escape. So this enables. And now we can create those pads in this layer itself, and we'll create them of length 10 micrometer and width is 25 micrometer. So let's enter the coordinates of there. 100, minus 11 and 110, 14. So this creates a pads here in the comb layer itself. So this is of the dimension 25 in y and 10 in the x plane. So we can take the mirror image again. So taking the mirror image, so we have 0, 26.5, 100, 26.5. So we take the mirror image. So we have created this, and then these are the hinges that we have created. So let's create the proof mass. So with the rectangle 110, 19, and then 230, 33.5. So this creates a rectangle. So I fit to the layer window. Then we create the same hinges which is on this side, on the either side as well. So we will take the mirror image of this. So first we select this and then we enter the values. Uh, we are drawing a mirror line on the y-axis. Is 170, 26.5. So it's on the y-axis. So I'll retain the x coordinate same and then enter some value of it. So we have a mirror image on the other side. So I press escape to deselect and press zoom to fit. So we have created the comb structure on. So we have created the hinges on either side. So let's create another rectangle. Uh, let's create the comb structures now. So let's get into this area. So here I select layer fill. So to have a clear look, and I go to create rectangle and then start entering the coordinates to create the comb structure. So the comb structures must be available here. So I enter these following values. 4, comma. We have created one of the strip which is of the dimension 2 micrometer on the X and 15 micrometer on the Y scale. So we'll create one more strip of this which makes a pair of comb. So we enter 136.5, comma 9, enter. -6. So this creates a pair. So the distance between the two combs is 0.5 micrometer. Hence this value here we have entered. So now we can create n number of combs using this, using the option called matrix array. So we enter 15 pairs, one row, and column spacing needs to be carefully selected. So here the column spacing goes like this. The width of one strip is 2 micrometer plus 0.5 micrometer gap plus another 2 micrometer. So it becomes 2 plus 0.5 plus 2. So it becomes 4.5. So plus additional of 0.5 gap. So it becomes 5. And row spacing 0. Click OK. So we get number of combs. And then I press escape. So this gets deselected. So this is how we create the combs. And we create the here we create one more anchor on either side to hold the other side of the comb. So we can either take a mirror image or we can create the rectangle separately. So here it's up to the user's comfort level. So here I use it using the coordinate system itself. I create the geometry to keep it more simpler. So we've created this rectangle now. So this is the overall geometry. So now we go to pads and then create a rectangle. So here we create them. So we select, we can take the mirror image. So we enter the x coordinate, can be 0, 26.5. So press escape. So now we have created this mirror image. So let's create another mirror image on the other side. So we draw this, we select both of them, 170, comma 26.5, enter. So we are drawing the vertical line. So 170, comma. So on the other side, the pads have also been drawn. So now we save this file. Once this is done, we can close Blueprint. So here we come to 3D Builder and then we can import the file that we have created. So I select Manhattan. So I select comb trial. This is the file that I've created. The layout, we had not defined any thickness in the layout section. So hence by default, the layer are 1 micrometer in thick. So we can also define the elevation and the thickness of each layer in Blueprint module. Here we can increase its height. So this creates the geometry. So here we make certain changes to define the entities. So here we need to define these are two different conductors. So naturally the entities of the two sides of the comb have to be different. So we can do that by selecting the portion and then change its color. So once this is done, so we can save this file. So we can retain the same name as the file formats can be different. And export this to analysis module. So this gets exported to analysis module. So here we can do the analysis. So let us perform frequency analysis simulation. So we set frequency. So material I can choose based on my choice. So for simplicity, I'll maintain it as silicon 100 everywhere. Go to loads. So here we don't apply any loads because we are performing natural frequency analysis to find the natural frequency of the device. So we go to fixed and then we click on these faces to fix the geometry. So these four pads are fixed and this side is also fixed. So we go to mesh auto. So we enter 10. So I am maintaining a very coarse mesh just to complete the simulation faster. So we can still refine the mesh based on the user's requirement. So I'll run the analysis. So simulation is complete. Go to natural frequency and we get three modes of vibration: mode 1, 2 and 3. So mode 1 is at 117.9 kilohertz. Mode 2 is at 272.7 kilohertz and mode 3 is at 294.332 kilohertz. So we can see the mode animation. So this is mode 1 of vibration. So we can stop the animation here and see mode 2. So here we feed the mode number and the scale factor. Scale factor is basically to emphasize on the displacement. In case if the displacements are too small, then to emphasize on the displacement, we enter the scale factor. But this generally does not increase the displacement, but virtually it will show us emphasized movement of the um, device. So this is mode 2 of vibration. So we can stop animation and then similarly mode 3 can also be extracted. So here in case if we require higher modes of vibration, then we can always set the number here and perform the simulation, which will give the n number of modes that we feed in as the value here. So here you can disable, enable mesh options, and to have more graphical oriented result, we can post process this results and see the results in the post processing. So here I select. So here I get mode displacement. So this is in one direction. So once, this is once. So we can loop this and click. So you can also set the contours if required, and you can set the number of contours as well. So by default it is always 11. So we can increase it to 100 so that we'll have better clarity on the result. So this can also be exported as a AVI file for animation purpose. So all the three results can be extracted here. So mode 2 of vibration. So here on the real time itself, we can emphasize on the displacement. So it's in this direction. Mode 2 is, the mode 1 is in this direction. So this is all about the frequency analysis simulation of a comb drive structure. So let's look at the electrostatic analysis in the next set of simulation. So once this is done, we close the uh, part. So we don't want to save anything. So now we'll perform electrostatic based simulation. So here we'll set this value, thermoelectromechanical relaxation, apply, OK. Material properties have already been set as silicon 100 to all the material. Loads, we had not given any load, so we'll set the potential difference between the two. So we'll set some value 60 volts and another electrode at 0 volts. So boundaries have already been fixed in the previous simulation. So we retain the same coarse mesh. We can do a refinement in the mesh here by selecting mechanical mesh, pick on geometry. So here we can set the value to be 5 micrometer, update mechanical mesh. So this refines the mesh in those region that we wanted, and then we can run the simulation, static simulation. The simulation is complete. So now we go to results and we can check x displacement, y displacement, and z displacement due to the voltage that we have applied. So if we want to see the animation, so we can go to linear motion, click OK. This shows a small displacement happening for the applied voltage. So this can generate the animation for us. So post process for visualize and opening the visualize, the data can be more graphical oriented. So this is how so this was an example on how to create a structure in IntelliSuite software and to run the simulation for a comb drive structure. So specifically these type of analysis is done for electrostatic based sensor or actuator devices. So it can be gyroscope, accelerometer, resonator kind of an application.